Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled as Crystal Growth Theory under paper Crystallography and Crystal Growth. In this module we shall learn about some theoretical aspects of crystal growth. Equilibrium form of a crystal on the basis of Kozal model is discussed. Simple cubic structure is considered in the discussion on determination of equilibrium form of crystals. Wolff's theorem is explained. The cube model to discuss ideal crystal growth is considered, and understanding of how a two-dimensional nucleus grows into a complete layer is given. It is explained that actually real crystal growth does happen under conditions in which two-dimensional nucleation is impossible. The growth of real crystals is explained on the basis of Frank's model of screw dislocation theory, which provides a source of never-ending, repeatable steps, thus accounting for the growth of real crystals at low supersaturations. Crystal growth due to a step provided by the intersection of screw dislocation on the surface of the crystal, which give rise to a crystal growth in a spiral form, is explained using schematic illustrations. Equilibrium form of crystals. Kozal in 1927 used a very simple model of a crystal to calculate relative surface free energies. The objective is to determine equilibrium form of a crystal, and in order to achieve it, one is required to find binding energy between the atoms. It is well known that the atoms of a crystal are arranged in a definite geometrical pattern in which each unit cell is periodically repeated and each atom has specific structural surroundings. The nucleation and growth processes of crystals depend strongly on the crystal structure. However, in the discussion on equilibrium form of crystals, we will use the simple cubic structure as shown in figure 25.1, in which each represents one atom and also one unit cell. Site marked 7 is incompleted edge. Site marked 8 is completed surface. Site marked 9 is completed corner. Site marked 10 is incomplete edge. And site marked 1/2 are half crystal positions, which are also known as kink sites. Figure 25.1 shows different atomic sites on the surface of a simple cubic structure. In this figure is shown an incomplete face, and there are various atomic sites designated by numbers with differing bonds of strength. Some atomic sites of significance may be identified here in the figure itself. Such sites are: site marked 1 is phase vacancy. Site marked 2 is edge vacancy. Site marked 3 is adsorbed atom. Site marked 4 is completed step. Site marked 5 is step edge. Site marked 6 is incompleted corner. In the simplest form of crystals, the binding energy between the atoms varies with 1/6 power of the distance between them. To understand this, one may refer to figure 25.2, which shows a simple cube model in which atoms are represented by cubes. The atoms, that's the cubes, are labeled as 1, 2, 3, and 4 and representing first, second, and third nearest neighbors of an atom, that is the cube. Suppose the centers of the two cubes, which share one face, are separated by a distance small d. In other words, the distance between an atom and one of its nearest neighbors, as for example 1 and 2, is small d. The distance between the second nearest neighbors, that is the cubes, joined at one edge, say 1 to 2, is under root 2d. The distance between the third nearest neighbors, say 1 to 4, of figure 25.2 is root 3d. Now, if two cubes, that is the atoms, are brought from infinity to a distance d from each other, the potential energy released is 5 by d raised to power 6. For the second nearest neighboring cubes, that's the atoms, 5 by 8 into d raised to power 6, and for the third nearest neighboring cubes, 5 by 27 d raised to power 6, and so on. Since the number of neighboring atoms at a distance, say r, increases as r square, while the force decreases as r raised to power 6, those neighboring atoms which are distant farther away do not influence the total binding energy much, and as such should be ignored. Now let us go to the interior of the crystal. Consider a cube. In the interior of the crystal, it has 6 nearest, 12 second nearest, and 8 third nearest neighbor. As argued above, neighboring cubes which are farther away are ignored for reasons given above. Therefore, the binding energy is 6 phi by d raised to 6 plus 12 phi upon 8 into d raised to power 6 plus phi upon 27 d to the power 6. The binding energies of cubes will depend on the position it is occupying on the surface. Referring to figure 25.1, the cubes are shown at different positions and are accordingly labeled by numbers. Some have one of their sides attached to only one face of the cube under it, say for example number 3. 5 faces of the cube attached to the faces of cubes on all the sides except the top face, say for example number 8, and so on. So the binding energies of each cube will depend on where it is placed. The interesting position is the king side, which is labeled as 1/2 and also known as half crystal site, as shown in figure 25.1. The binding energy of a cube at the king site is exactly half the total binding energy of an interior atom. The addition of an atom to a half crystal position creates another half crystal position to which an atom can be added. On a kinked step, atoms can continually be added to the half crystal positions on the plane and create new half crystal positions as the crystal grows plane by plane. On a kinked step, atoms can get attached at the kink site until the row of atoms gets completed. Except for the first atom of each row, a complete plane can be built up by successive additions at half crystal positions. The relative binding energy of a cube at the kink site is given by 3 phi over d raised to power 6 plus 6 pi over 8 into d raised to power 6 plus 4 pi by 27 d to the power 6. This is exactly one half of the binding energy of an interior cube. At equilibrium, an atom at the kink site, that is the half site, has the same probability to evaporate as is for an atom to condense at the adjacent empty half site. It is easier to remove cubes, that is the atoms, which are not that strongly bonded as those positioned at the half site, and therefore cubes, that is the atoms, get added up in sites where they would get as strongly bonded as the one at the kink site. This is how the building of equilibrium form of a crystal may be thought of. However, this method does not directly lead us to the equilibrium shape of a crystal. It also does not provide any lead to knowledge regarding ratio of the areas of various phases at equilibrium. Using certain appropriate assumptions, it is used to calculate interfacial energies for different phases, which can then be used along with Wolff's law as described below to provide a lead in giving equilibrium shape of a crystal. Wolff's law. Wolff's theorem states that in a crystal at equilibrium, the distances of the phases from the center of the crystal are proportional to their surface free energies per unit area. Wolff's law is aimed at determining equilibrium form of a crystal from known interfacial energy through geometrical construction. The interfacial free energy of every possible phase is taken as a vector originating from the origin, with length of each vector made proportional to the interfacial free energy and directed perpendicular to the phase is plotted. The curve so drawn, connecting the ends of these vectors, lead to formation of cusps. Each phase is then drawn at the position of its cusp, and the equilibrium form is given by the interior figure so obtained. This is known as Wolff's construction of equilibrium form of crystals. This construction is precisely correct and as such assumes great theoretical interest and importance. The crystal model as given by Kosal offers a realistic picture of crystal surfaces only at low supersaturations, at low temperatures. However, at high temperatures, the thermal vibrational energy of the cubes, that is the atoms, is called into play, which cannot be ignored and has to be included. Ideal crystal growth. To explain crystal growth, we will consider the cube model shown in figure 25.3. Figure 25.3 shows a schematic diagram showing cube model. We start with a perfect crystal, which is in its equilibrium form. Under isothermal conditions, growth of the crystal will take place if it is subjected to a supersaturated environment. The process is accompanied by a decrease in free energy, and the crystal struggles for growth. The growth has to happen atom by atom or molecule by molecule. In the cube model of figure 25.3, each atom or molecule is represented by a cube. For the addition of first atom, the most preferable site is the center of one of the faces. However, the attachment at this site is not very stable as it is bonded less strongly as compared to the king site. At the king site or the half crystal site, the atom or molecule is much more strongly bonded than any other site. Unless there are thermal fluctuations, the process of crystal growth cannot start. Figure 25.3 is a cube model which shows the structure of a phase under a situation where thermal fluctuations exist. Single cube, that's the atom, at an isolated site on the surface is far less stable than two cubes, that's two atoms, in contact. The cube, that's the atom, at the king site is far more stable than anywhere else. The process of transitory groupings of additional atoms and of vacancies, that is the holes, exists. In this way, the crystal phase, after completing a layer, must add complete new layers. The initiation of a new fresh layer is a problem of nucleation. The problem is that of what is called two-dimensional nucleation. The growth of nucleus in this case takes place by a process shown in figure 25.3, which is a schematic diagram showing a cube model. The process is that of migration of cubes to sites where they are more strongly bonded, a process which involves migration of atoms, say at the place labeled number 1 to position 1 prime, 2 to 2 prime, 3 to 3 prime, and so on. This is how a layer keeps on building up. For a two-dimensional nucleus in the form of disk of radius r and height d, the free energy of formation is delta F equal to Fc minus Fe into pi into delta r square into d plus twice sigma pi into delta r into d, where Fc minus Fe represents free energy change in crystallization and sigma is the surface free energy. The subscript E here in the above expression stands for environment. In the formation of this disk, the excess surface grown in circumference times the height d and the critical radius r star associated with the maximum value of delta F, that is F star, is sigma upon Fe minus Fc. In considering growth of crystals, it is important to understand how a two-dimensional nucleus grows into a complete layer. Any incomplete step has a kink associated with it, and atoms migrating to kink sites are stable. This way, the step becomes complete as fast as surface atoms migrate to kink sites and get attached there. Thermal fluctuations create situations that lead to a steady concentration of kinks in any step. Nucleation of new rows of atoms can get so rapid that it is of no consequence in step growth. A perfect crystal cannot grow at all until the supersaturation is more than some critical value. Boehmer and Schulze performed experiments to test two-dimensional nucleation growth theory by examining the growth of iodine, phosphorus, and naphthalene as a function of supersaturation. They observed that the growth rate was much higher for iodine at saturation value far below what was expected from the two-dimensional nucleation theory. They found that the growth rate of iodine was high at saturation values at which they expected it to be negligible. Vollmer and Schul's experimental results required an alternative source of growth centers. The explanation offered by Frank was screw dislocation growth, discussed in the section that follows. Real crystals grow under conditions in which two-dimensional nucleation is impossible. The creation of a step on perfect crystal surface due to coalescence of several isolated atoms which are randomly deposited from the liquid or vapor phase is an event of a very low probability, because such atoms are not very strongly bound to the crystal phase and do not usually remain attached to the crystal long enough to join up the formation of a growing step. These atoms are usually removed by thermal agitation before they are able to do so. However, if a step is formed in this manner, it will then rapidly spread across the crystal face by the addition of atoms at the edges where they are strongly bound. This may continue until a new atomic layer has been added. Further growth then takes place only with great difficulty, since a new step is required to be formed on the added layer. It was Frank who suggested that screw dislocations having a displacement vector parallel to the crystal face would provide a source of steps which would persist and never disappear. Screw dislocation becomes a source of repeatable steps. In order to understand as to how screw dislocation becomes a source of perpetual step with the help of which the crystal can grow, we need to relook at the formation of this type of dislocation. Consider a crystal in which a cut X, Y, Z, K is made partway on its surface, and one of the two sides of the cut is pressed so as to cause their displacement relative to each other by one atomic spacing in the direction shown by the arrows in figure 25.4a. Since the displacement is by exactly one atomic spacing, the vertical faces of the crystal stay perfect and the imperfection is confined to the cylindrical volume xk as is shown in figure 25.4b. The steps xy and zk can never disappear either as a result of growth or by dissolution. The top and bottom surfaces will always remain imperfect and can never be perfected. It is much easier for a crystal to grow by diffusion of extra atom to the step of a screw dislocation than by spontaneous addition of atoms to perfectly flat crystal surfaces. Addition of atoms at the step of a screw dislocation cannot destroy it. It simply sweeps round the actual point at which the screw dislocation intersects the crystal face, rather like the beam of lighthouse which sweeps round. Figure 25.5 is a schematic diagram showing crystal growth at a step anchored at a screw dislocation. which results in a spiral formation. On account of the fact that the step xy is anchored at point x, and because the step will grow by surface diffusion at the same rate during growth, this step must wind itself up around the point x into a spiral as shown in figure 25.5. This is how Frank's model of real crystal growth resolves the fundamental discrepancy between theory and experiment. Most real crystal growth does not require two-dimensional nucleation and spreading of layers. This is how spiral growth was predicted on theoretical reasoning by Frank in 1949. Practically, spiral pattern of the growth was first observed by Griffin in 1950 on the surface of a beryl crystal. Later, spiral patterns were also observed on large number of crystals like silicon carbide crystal by Verma, quartz among many other crystals. Through measurements, it has been shown that the height of the steps grown is of one atomic or molecular size. Let us now summarize of what we have discussed so far. Theoretical background of how crystals grow is considered. Equilibrium form of a crystal on the basis of Cosel model is discussed. Equilibrium form of a crystal is discussed on the basis of simple cubic structure. Wolff's theorem, providing important inputs in determining the equilibrium form of crystals, is explained. Process involved in nucleation and completion of layer on the surface of a perfect crystal is discussed. It is explained that actually real crystal growth occurs under conditions in which two-dimensional nucleation is possible. Growth of crystals at low supersaturations is explained on the basis of Frank's model of screw dislocation theory. It is explained that screw dislocation emerging on a crystal surface provides a perpetual step which never ends, as a result of which adsorption of atoms along the step occurs at lower supersaturations and growth of crystal can take place continuously. This type of growth, leading to formation of spiral steps on the growing crystal surfaces, is explained and illustrated with the help of a schematic diagram. The screw dislocation theory of crystal growth is supported by observation of spirals on different crystal surfaces by several researchers. Thank you.